In this video, we will talk about statistical associations. I want to give you a sense of what this means and what they look like before we go on to any actual statistical analyses. So there are several words you can use to refer to statistical associations, and they all essentially mean about the same thing. The first and simplest word is relationships. So two variables can be related, or there is a relationship among variables. The forms that relationships can take depends on the measurement scales of the variables. And we will see some examples about different kinds of scales. When the variables are numeric or quantitative, the relationships can be linear or proportional, which means the same thing, or they can be nonlinear. And we will also see some examples of what that means. Another word we can use to describe statistical associations is the word effect, which in statistics means the same thing as a relationship. So the strength of a relationship is termed effect size. Actually, effect sizes have more specific meanings depending on the type of test, and so they can be precisely calculated as quantities, or they can be characterized as small, medium, or large. Another word that we use to refer to the same idea is prediction. This means that if two variables are related, then you can predict one based on the other. And of course, you cannot predict perfectly because the two variables aren't measuring exactly the same thing, but you predict to some degree. And how far off you predict is your prediction error, which is also called a residual. So residual is a measure of how far off your prediction is when you use one variable to predict the value of another. One final term that is used is shared variance or common variance. So the idea here is that two variables that are related have some common variance. That's what the relationship consists in, that changes in one variable are associated with changes in the other variable. That's why they're related. And the degree to which these changes are consistent and proportional is reflected in the proportion of variance that is shared between these two variables. So a simple way to think about statistical associations is by imagining a guessing game. The guessing game is a game where you have values from one variable and you see if you can use those to improve your guessing of the values of another variable. Let's start with an example using two qualitative or categorical variables. Let's say we are outside a high school, a videregående skole, and we just pick a random student who is walking there from the vocational program. Try to guess this random student's sex. Is it a man or a woman? What should you answer? If you knew the proportion of women attending vocational programs in high school, then that should be your answer. And that would also indicate how often you would be guessing correctly. Now think of the variable specialization. So which actual study program have they chosen? Would that help you guess any better? If it does, then it means that sex and specialization are related variables. Let's look at some actual data. So it turns out that in 2019, the proportion of women attending vocational programs in high school in Norway was 42%. So if I picked a random student and asked you to guess the sex, you should guess man because you would be right more often than you would be wrong. However, look at the variation among the different specializations. So construction and electricians have very low percentages of women, whereas design and health-related occupations have very high percentages of women. So this means that if you knew the study direction of the random person I picked, you could guess the sex with a higher probability of guessing correctly. It means that the variable specialization, so which of these directions the person is attending, so this variable helps you predict the sex variable more accurately. So the two variables are related. What does this look like in a graphical form? So this is a mosaic plot that plots sex against specialization. And so this column here indicates the men, and this column here indicates the women. And you can see that the column for men is wider because there are more men in the vocational programs than there are women. Okay. The important property here is that the area of each of these rectangles is proportional to the number of people of the corresponding sex attending that study direction. So we can see that the area of the rectangle for construction for men is much larger than the one for women. And the rectangle for electricians is also much larger than for women. But the rectangle for health-related occupations is way larger for women than for men. And the fact that these sets of rectangles look so different in their sizes indicates that the proportion of women varies widely between different study directions, which is a visual way to say that the variables specialization and sex are related in the sense that knowing one helps you guess the other one more accurately. And this works both ways. So if I pick a random student outside a high school and ask you to guess their specialization, what are they studying? Of course, you can try to guess based on the overall proportions, but then would your guess be different and more accurate if you knew the sex? So if I told you this random person is a man, you should probably not guess that they're studying design or health, although of course there are plenty of men who do take these specializations, but there are many more men who have chosen other specializations. If I told you that the random person is a woman, you should probably guess that they are in the health-related occupations specialization, because that is the study direction with most women. So the fact that knowledge of one variable would make you change your guess on the other variable means that the two variables are related. And this is the visual display of two related qualitative or categorical variables. Let's see what the guessing game looks like for different kinds of variables. So now let's go to numerical or quantitative variables. Let's go outside an elementary school now and pick a random kid, one pupil. Guess their vocabulary score. That is, guess how many correct answers they will get in a test of receptive vocabulary showing them pictures and saying a word, and they have to choose the correct picture that corresponds to the word. So how would you do that? Would knowing the age of the child help you guess more accurately? Here is what the relationship between these two variables looks like. On the horizontal axis is the age of children in months, and on the vertical axis is the number of correct answers on this vocabulary test, so their vocabulary score. You can see that this graph indicates a relationship in the sense that there aren't many low scores for older children, but there are many low scores for younger children. And there aren't very many very high scores for younger children, whereas there are many high scores for older children. So there seems to be a clear relationship between age and vocabulary. If you have to guess the vocabulary of a child, a random child, about which you know nothing, then your best guess would be the mean vocabulary score, which is about 122. And that should be your answer, because that would minimize your error. That would minimize your long-term distance from the correct answer, how far off you'd get. So this would be your best bet. However, if you knew the age, then your prediction should be different. If you knew that the age of the child was 8 years, or that the age of the child was 12 years, then your guess of their vocabulary score should be very different because of this relationship. As you can see, for an 8-year-old, most scores are between 70 and 140, and the mean for 8-year-olds is about 105. In contrast, scores for 12-year-olds are between 120 and 150, and the mean is just above 140. So if the random kid was 12 years old, you should guess 141. If your random kid was 8 years old, you should guess 105. And that precisely reflects the relationship between age and vocabulary. Again, this works backwards as well. If I said, here is a random kid, can you guess their age? You should guess the average age for kids going to elementary school. But if I told you that the kid's vocabulary score was 140, you should not guess the average age. You should guess the age at which 140 is an average score. So you should probably guess around 12 years old and not around 8 or 10 years old. One final guessing game we can play is with one quantitative and one qualitative variable. So one categorical and one numeric variable. So now let's stand at the university campus and pick a random person. Guess how old they are. If I tell you whether this person is a student or an employee, would you still guess the same age? You probably shouldn't, because these two variables are related. Let's look at just one way this can be visualized, and later we will see more ways for this combination. So these are actual data for all Norwegian universities, employees versus students by age range. And we can see that most students are less than 30 years old, and you should probably guess their age in the 20s, whereas most employees are older than 30 years old, so you should probably guess an age in their 40s. That's because the two variables, age and status, are related. And again, it works the other way as well. So if you were to guess whether a random person on campus is an employee or a student, would it help you to know the age? It would, because the variables are related. So any age below 55, and you should guess it's a student, because students are more than employees for all of these age ranges, except for the ages between 55 and 69 when employees clearly outnumber students. And so if I told you this person was 60 years old, you should guess employee. If I said the person is 35 years old, then you should guess student. And that's because two variables are related. And when two variables are related, it means that each of them can help predict the other one better. Let's look at some properties of statistical associations involving quantitative variables, namely linearity and strength, what this means and what it looks like. This is a measure of word reading efficiency, the number of words read correctly within 45 seconds, as a function of age, from 88 through almost 150 months. So these are for children. Again, we see that we have a lot of lower rates for the younger kids and not very high rates for young kids, and higher rates for the older kids, and not very many low rates for the older kids, because of course kids read faster as they grow up and become more experienced and skilled readers. So the relationship between age and word reading efficiency looks like a band of values that is sloping upwards. And it's very clear in this graph by the relative lack of data points in this corner and in this corner. The actual shape of this relationship appears to be close to a straight line. So I can draw a straight line going through these points, and it would seem to go through the points at all age levels with a similar success. That means that it leaves about as many data points above as it does below. So here we have a relationship that appears to be linear. Linear means proportional. It means that equal changes in age are associated with equal changes in expected performance in word reading efficiency. The fact that this band is relatively near the straight line suggests that the relationship is strong. This means that if you know the age of a child, you will not make a huge mistake predicting their actual performance. Of course, there is a wide range. So a child at 100 months of age can have as few as 20 words read or as many as 80. So that is a big range, but most of them are between 30 and 55. So if you guess the mean performance around 50, then you're not going to be far off for most children. And you shouldn't guess 55 for a child that is 12 years old, because then you would really be very unlikely to get it right. You should guess something more like 70, and then you'd be near most actually observed scores. So this is what a linear, strong relationship between two numerical variables looks like. What about a measure of reading comprehension for these same children? Well, again, we can see that there are few points here, which means that there are few older kids with very low scores. Low scores now mean few questions about the meaning of the passages answered correctly. This is a reading comprehension test. So low scores mean that you answer incorrectly the comprehension questions. And there are also somewhat fewer very high scores for the youngest children. But we see that the shape of this relationship is very different from the previous one. It's different in two ways. The first way in which it's different is that the band or the range of performance is very much wider. So if you know the age of the child, you can still make a better guess than without the age, but the improvement from knowing the age would be smaller. So you can guess 11 correct answers for a child at 90 months, or you can guess it for a child at 120 months. And although it's not optimal in either case, you would not be making a huge mistake for many children. And the difference between the score you'd guess for a young child and a much older child would be much smaller. So this is a weaker relationship indicated by the scattered values in this graph in comparison to the condensed values of the previous graph. It's also different in one more way, in that we shouldn't fit a straight line here. If we try to fit a line that goes through the average performance at each age, we will see that the best line would not be completely straight. This line isn't going straight up like the previous one. Instead, it's decelerating. It's increasing less and less steeply with higher ages. And that's in large part because there is only 18 questions to this test. So older kids tend to answer them, or almost all of them, so there's not much room to grow. But here the question is about the relationship, not about its cause. So it looks like this relationship is not exactly linear. It's not proportional. The change in expected score between a child from 90 to 100 months old is more than the expected change for a child going from 130 to 140 months old. So the expected change here is less than the expected change here for the same amount of time. So this is not a straight line, and this is called a curvilinear relationship. And it's a curvilinear weak relationship. And we can look at the two graphs side by side. So this is reading comprehension by age, and this is word reading efficiency by age. And you can see that they're different in shape and in how spread the points are. We can plot this relationship in a different way if instead of using the age, let's say we didn't have the actual age of the children, but we just recorded their grade, what school grade they were going when they were measured. This is not a continuous variable. There is no grade 2.5, so you go from 1 to 2. So these are categories, order categories at equal distances. So this is an interval scale variable, but there aren't any continuous values. So it's much more informative to plot them using box plots. And we can see that the boxes for comprehension are much higher, much taller, indicating a larger spread of values in comparison to the range of changes observed relative to the fluency boxes. And we can also see that the rate of increase for the medians, which are displayed here, seems to be decelerating more strongly for comprehension than word reading efficiency. Actually, using this graph, we can see that in fact, neither of these two relationships is exactly linear because there is a slight deceleration for word reading efficiency as well. So as children grow older, the rate of increasing fluency becomes a bit smaller. So they improve at increasingly slower rates to some extent. But this effect is larger for comprehension, which seems to deviate more from the straight line because the shape of the boxes also changes. So these boxes are much taller than these boxes, which is not the case in the word reading efficiency graph. So this is a more clearly nonlinear relationship, and this is also slightly nonlinear. when you look at it in this graph. Let us see what differences between specific categories look like and how you can evaluate the relationships between variables using a box plot. If you don't remember exactly what the box plot shows, please go back and review the information about the box plots. Here is the graph of word reading efficiency by grade. And we can see the boxes enclosing the half of the data by showing the first, second, and third quartile. Let us concentrate on the difference between second grade and third grade. Is there a relationship between grade and word reading efficiency for this subset of the data? So just for grades 2 and 3, is there a relationship between grade and word reading efficiency? Does it look like we can predict one from the other? The box plots help us evaluate that by focusing on the indicated lines. So these two boxes are actually quite far apart, as you can see by comparing the median for grade 3 to the third quartile for grade 2. You see that this line is actually a bit higher. This means that half of third graders have higher word reading efficiency than 3/4 of second graders. So this is 75% of second grade data below this red line. And this is half of third grade data above this red line. So this is a substantial difference in proportions, which is consistent with the relationship among these two variables. It means that you can use one to predict the other. And this looks like a clear difference between grades 2 and 3. What about grades 5 and 6? Is there a clear difference? This time we see that it's only the median that's above the median, and so we can say that 50% of 6th graders read with higher efficiency than 50% of 5th graders. So this doesn't look like as clear a difference as the one between 2nd and 3rd grade. However, there are more points we can visually compare. If we look at the relationships between the first, second, and third quartile for these two groups, we see that for grade 6, they're all higher. So this box and all of its parts for this box plot is systematically above this box and its parts. So all the quartiles are for grade 6 are higher than the corresponding quartiles for grade 5. And this suggests that there probably is a relationship between these two variables that can be discerned if the samples are large enough. So if we have enough 5th graders and enough 6th graders, so if we have lots of kids, this situation here suggests that there probably is a relationship between the two variables, although it's not as clear as the one between the 2nd and 3rd. Let's look at the other variable, reading comprehension. Are there differences between specific grades? What about between grades 3 and 4? Well, here we see that the box plot for grade 4, actually the middle 50%, falls within the range of the middle 50% for 3rd grade. So the difference is even less clear if it exists. these two box plots are not suggestive of a clear difference. Now, if we look at the individual lines, we see that the first quartile and the median are higher for grade 4 than for grade 3, which suggests that there might be a relationship between these two variables for these two grades, but it's not very clear at all. And the third quartile is exactly the same. So this is a slight possibility for a relationship, and it would really depend on having a lot of children in order to be statistically discernible. Let's contrast this situation with a comparison between grades 2 and 6. In this case, we see that 70% of 6th graders score higher than 70% of 2nd graders. So if we only had these two boxes to work with, we would say that there is a very clear difference, or otherwise a very clear relationship between grade and reading comprehension, that there is an effect of grade on reading comprehension, or that there is shared variance between grade and reading comprehension. Let us now go back to look at how different strengths and directions of relationships appear on scatter plots. Here is a plot of word fluency, so words read correctly per minute, as a function of number of spelling errors on a spelling test. We see that there aren't any points here in this corner, and there aren't any points in this corner, but there are plenty of points in this corner and in this corner. Indeed, the points are relatively clustered around an imaginary line going like this, which is consistent with a relatively strong relationship between spelling and fluency. More specifically, we see that higher word reading efficiency or higher fluency is associated with few spelling errors. This makes a lot of sense. It means that kids who read more efficiently are also better spellers. And this is what this graph shows us. There is a clear relationship between spelling and word reading efficiency or fluency. And we can see that this relationship is negative for these two variables. Negative means that as one variable increases, the other variable decreases. So as the variable number of spelling errors gets higher, the variable words per minute gets lower. These are data for one grade only. These are only for third grade kids. So this is not an age effect. It's an effect of reading and spelling skill. And it shows that more spelling errors as well as lower efficiency in word reading are associated and are both indices of reading and spelling skill. This is the corresponding graph for the relationship between the variable reading comprehension score as the number of correct answers to comprehension questions, and again, number of spelling errors. Again, we see that this looks like a negative relationship, so that there are points here. A large number of spelling errors seems to be somewhat associated with a lower score on comprehension, and a low number of spelling errors seems associated with a high score on comprehension. There aren't many points in this corner. However, these points are much more scattered. They're spread over a much larger range. So this is not a very strong relationship. It's a weak negative relationship between the variables of spelling errors and number of correct comprehension answers for third graders. Here is another pair of variables. On the vertical axis here, we have the same fluency metric, so words per minute or word reading efficiency. And on the horizontal axis, we have the vocabulary score, so number of pictures correctly chosen for the spoken words. We don't really see much of a relationship here. It's not really the case that there are many points in only two of the four corners. And we don't see a very clear shape formed by these points. They seem to be scattered all over the panel. Maybe there is a few more points around the top right corner, but if there is a relationship, it's a really, really weak one. In contrast, if we plot comprehension by vocabulary, so the horizontal axis is again the number of correct pictures chosen in the vocabulary test. And the vertical axis is the number of answers, of correct answers in the reading comprehension test. We see that there aren't many points in this corner or in this corner. There are plenty of points in this corner. And there are also some points down here. The spread of these points is substantial. So this is not a very strong relationship, but still, it's a clear relationship between vocabulary and reading comprehension. And there is actually a quantity that we can calculate based on these points that expresses the strength of the relationship. It is called correlation, and we will talk about it more specifically. It is called correlation, and we will see it in more detail later in the course. For now, it's enough to say that it goes from -1 to 1, that 0 means that there is no relationship between the variables. -1 means perfect negative relationship, and +1 means perfect positive relationship. So the correlation values for these sets of variables range from 0.15, which is a very low value. It's near 0. It's a slightly positive relationship, but it's really very low. The largest value here is 0.71, and it's negative. It's minus 0.71, indicated that there's one variable increases, the other variable decreases. Hence, this is sloping downwards in the panel. The relatively large value here is consistent with these points being clustered around an imaginary line rather than spread over the whole panel. And the other two cases are intermediate. So this is a low to moderate relationship between spelling and comprehension, which is negative. So more spelling errors are to a slight extent associated with fewer correct responses to the comprehension questions. And a moderate to strong relationship between reading comprehension and vocabulary, which is a positive one, as higher vocabulary scores are associated with a larger number of correct answers to the comprehension questions. So this is a representative range of strength and direction for relationships among pairs of quantitative, that is, numerical variables. Here is one final case. This is time looking at a new word while reading. So these are from kids in grade 5 reading sentences in which there are some made-up words they've never seen before, but they encounter these same novel words in several sentences. And we use eye tracking to measure how long they look at each word. And we plot the duration of their gaze. So this is 1 second. It's 1,000 1/1000th of a second. So this is 1 second, this is 2 seconds. And we plot this variable as a function of how many times they've seen this new word. So 1 is the first time they encounter it, and then it's the second time and third time up to 6 times. Is there a relationship between repetition, how many times they've seen the word, and gaze duration, how long they look at it? There seems to be a relationship because we can look at the difference between the first and second time they see the word, and we can see that the lines that join the corresponding quartiles are all sloping downwards, and it looks like half of the data for the first encounter are higher than almost 3/4 of the data for the second encounter, almost. So this is a relatively clear difference between the first and the second time you look at a new word if you're in 5th grade. If you look at the difference between the second and third time, it seems smaller than the preceding one, but probably there, although it would require a relatively large number of data points to statistically verify that it exists. The situation is less clear for the difference between the third and fourth repetition. So here it seems to level off. There may be a bit of a difference. So you may be getting a bit faster in the fourth encounter, but it's certainly not very big and may not be statistically reliable. After the fourth encounter, there is really not much evidence for a relationship. This looks like a bit of noise there. Lines go a bit up or a bit down. The different quartiles aren't coordinated. So it looks like once you've seen a new word 4 times, you don't get any faster. And we can visualize the whole relationship using a smooth curve of this kind of shape, which shows 2 things. The first one is that this curve is sloping downwards, which is a negative relationship. So the more times you've seen the word, the less you look at it. One variable increases, the other variable decreases. So this line is sloping downwards. The other is this line is not straight at all. It's markedly curved, so the differences between the first couple of encounters with the word, a new word, are much larger than any differences further down with subsequent encounters. So this line is leveling off. So this is a curvilinear negative relationship between the number of times you've encountered a new word and the time you spend looking at it. And that's the kind of information that you can visually obtain by looking at a box plot like this. So when we talk about relationship types and shapes, the things that you can evaluate graphically include whether the relationship is linear, this means proportional, or if it's nonlinear, so it may be curvilinear, maybe the line that indicates the relationship between 2 variables is curved instead of straight. There can be a strong or weak relationship, which is indicated by the spread of the data points on the 2 variable graph. And it can be a positive or a negative relationship, indicating whether the 2 values increase together or whether increase in one variable is associated with a decrease in the other variable. And these are all things that you can get from looking at graphs plotting 2 quantitative variables. To sum up, and taking into account all the different kinds of variables, as we've said before, statistical analysis always concerns associations among 2 or more variables. Indeed, all quantitative research questions concern associations among two or more variables. There are several different words that essentially refer to the same idea, the associations between variables. And these are a relationship, an effect, a prediction, or shared variance. And all of these can be used in both directions. And all of these can be used in both directions. So associations between variables are statistically bidirectional. Statistics isn't telling you which variable affects the other. It's telling you how confident you can be in whether the two variables are associated, in whether the two variables change values in somewhat systematic or consistent ways. These four different words referring to statistical associations also express the idea that relationships can vary in strength, or effects vary in size, which is the same thing, that are consistent with different proportions of shared variance or different magnitudes of prediction error. Using graphs of our variables, we can detect any potential problems with the data, and we can also detect the extent to which there may be relationships between our variables. And we can have a first impression of the type, the shape of relationship, and the strength of a relationship. However, we can never draw a conclusion based on that. We always need to conduct formal statistical analysis in order to quantify the effect size, so find out exactly how strong the relationship is, and also calculate the confidence, how confident we can be in that there is a statistical association between these two variables.